Welcome to today's Explainer. We are diving into a topic that honestly sounds a bit like magic, but it is actually deeply elegant foundational science. Today, we're exploring the surprisingly high-tech world of planar chromatography. To make this really click, I want you to imagine a microscopic race. Picture an obstacle course where the competitors are completely invisible to the naked eye. Sounds cool, right? Let's get into it.
Think about this for a second. If you have just a single drop of a really complex biological mixture, or maybe a chemical solution, how do you pull it apart? How do scientists perfectly separate all the invisible ingredients hidden inside that one tiny drop of liquid? It kind of seems impossible without, massive room-sized machines. But what if I told you that one of the most powerful ways to pull this off involves literally just a glass plate and a shallow puddle of solvent?
So, here's our game plan for today. First, what exactly is planar chromatography? Second, preparing the TLC race. Third, revealing the invisible spots. Fourth, the 2D chromatography twist. And finally, calculating the retention factor.
Section 1. What is planar chromatography? Okay, to understand how this works, let's build that obstacle course we talked about. First up, we need a track. In TLC, thin layer chromatography, this track is called the stationary phase. It's usually a small rectangular plate made of glass or aluminum, coated with an incredibly thin film of silica gel. We're talking just 100 to 200 micrometers thick. Next, we need our driving force, the current. This is the mobile phase, which is a liquid solvent. And finally, we have our runners. These are the actual sample components that we want to separate. When the liquid sweeps over the silica gel track, it carries the runners along with it. But because of the chemical properties of that track, some runners stick and slow down, while others just glide right on through.
Now, you might be picturing a scientist with a really shaky hand using a tiny glass tube to set this up. But modern technology has actually evolved this into what we call nano-TLC, using highly programmable machinery. Take the ATS-3 applicator, for instance. It automatically deposits a sample in exact microscopic bands or spots. This high reproducibility is a total game changer. It transforms TLC from just a simple visual check into a rigorous quantitative method of analysis. Moving right along to Section 2, preparing the TLC race.
The setup here is remarkably straightforward, but it relies on some absolutely brilliant physics. Step 1, we deposit our sample spot exactly 1 centimeter from the bottom of our silica-coated plate. Step 2, we place this plate into a covered chamber that contains just a few millimeters of our liquid solvent. Now, step 3 is where the physics completely takes over. We don't pump the liquid up the plate, it climbs up completely on its own through capillary action, pulling our sample components with it at totally different speeds. And finally, step 4. Once the solvent has traveled a few centimeters, we pull the plate out and let that solvent evaporate.
When the plate is sitting in that vertical chamber, the liquid slowly creeps upward, causing that differential migration of the compounds we want. And here is a super fascinating detail from our source data. If the liquid mobile phase contains water, scientists will often add salts to it, like sodium chloride or lithium chloride. Why? Well, it actually limits diffusion phenomena and really tightens up the resolution. Basically, it forces the runners to stay right in their own lanes.
Section 3, revealing the invisible spots. So how exactly do you score a race when you literally can't see the competitors? If the compounds are colorless, we actually have to force them to reveal themselves. We do this in the post-chromatography development phase using sheer chemical ingenuity. Sometimes, manufacturers will mix a fluorescent zinc salt right into the silica gel track itself. If you shine a UV mercury lamp over it, the whole plate glows, but the separated compounds block the light, making them appear as dark spots. Alternatively, we can use chemistry. We can spray the plate with sulfuric acid and heat it up to literally carbonize the compounds, turning them stark black. Or, we can use general reagents like phosphomolybdic acid, or even highly specific ones like ninhydrin, which specifically reacts with amino acids to introduce a bright visible color. Just like that, the invisible becomes visible.
Section 4. The 2D chromatography twist.
Imagine you run the race, but 2 of your runners cross the finish line at the exact same time, stacked right on top of each other. You can't tell them apart, right? Well, two-dimensional TLC solves this beautifully by using a square plate. After the first race, you dry the plate, rotate it exactly 90 degrees, and run a second race using a completely different liquid solvent. Let's say after the first run, a couple of compounds are just mashed together. They haven't separated at all. But by turning the plate a quarter turn and bringing in solvent number 2, we force them to run along a brand new axis. Because that new solvent interacts totally differently with the molecules,
those stuck compounds finally drift apart. This technique is an absolute lifesaver for pulling apart highly complex mixtures, like when you're trying to isolate specific amino acids.
Section 5. Calculating the retention factor.
To mathematically score this whole process, chemists use a metric called the retention factor, or RF. It essentially compares the distance the sample traveled against the distance the liquid solvent traveled. And as our source points out, grabbing precise measurements like this is exactly what elevates TLC from a quick visual check into a highly rigorous, quantitative method of analysis using modern instruments.
In quantitative analysis, scientists are always looking for specific mathematical sweet spots. Often, they are aiming for an RF value right around 0.3 to achieve the absolute maximum resolution between compounds. Getting this level of reproducible, precise data is exactly why those automated applicators we talked about earlier are so crucial today.
Now you might be wondering, why even use this simple plate method instead of massive, expensive HPLC machines? Well, let's compare them head-to-head.
While TLC and HPLC actually share the exact same core principle of separation, our source vigorously defends TLC for its incredibly high capacity. Because you can deposit multiple spots, or even horizontal bands, all at the same time on a single plate, it analyzes samples significantly faster, up to 4 times more sample in the same period. It's a highly efficient, single-use quantitative method that absolutely holds its own against much more complex instrumentation, completely eliminating the risk of cross-contamination along the way.
Which leaves us with this final thought. If the silent, upward pull of capillary action on a simple glass plate can perfectly isolate the invisible complexities of our world, and do it efficiently enough to rival complex machinery, what other elegant, unseen physical mechanisms are quietly shaping modern science? Thank you so much for joining me for this explainer. Keep asking questions, and I will see you next time.